Okay, it's time to get started. So let's begin the next unit. It's segment 9. We're doing lesson 1, chemical thermodynamics. One of the important things, if not the most important thing about thermodynamics, is to understand what state functions are. State functions are quantities that have a unique value independent of the path you use to reach them. Let's illustrate this with a little green box on top of a bigger orange box with a little ramp attached to it. We can consider the green box on top of the orange one as state 1. And I'm looking at the potential energy that that little green box has at each position and the amount of work that's being done as you move from this position to something else. So we're looking at both the potential energy and the work in this process. One of the ways we can move that green box down to the bottom is slide it down the ramp. And as we do that, you notice each time the potential energy is going down because it's not as high up in the gravitational field. And it has done some work in sliding down that block. Or think about friction, keeping the box from moving. So as it slides down the box, the potential energy goes down and the work that's done going up. And it's by the same amount. And when we get to the bottom, we've changed the potential energy. We've converted all of that potential energy into the work of moving that box down the slide. The other path is to just drop it off the top. So if I drop the box off the top, it falls to the bottom and it breaks up. But notice in this case, no work was done. Now, that's the important thing that we talked about with work once before. In order for work to happen, you have to have an opposing force. As we went down the ramp, the opposing force was the friction. When we fell off the side, assuming there's no air friction or anything like that, there was no resisting force. Work isn't done unless there is a resisting force. So there's no work done in the second path. But notice the internal energy was the same both ways. Internal energy is a state function. It's the same whether we go down the ramp or whether we go off the side. The path doesn't matter. It's just where you start and where you stop. The nice things about state functions is that you can just subtract the two endpoint values to get the change that takes place. Now, how do you define the state function within a system? The state functions are defined as intensive variables. Now, intensive variables don't depend on the amount of the sample you use to measure it. For example, think about mass of a sample and the temperature of a sample. The mass is not an intensive variable. It's what we call an extensive variable because it depends on the amount of matter. So if you've got 1 nickel and you're weighing it, it'll be 5 grams. You got 2, it's going to be 10. 3 is going to be 15. You see, it is going to depend on the amount of material. But if I measure the temperature of a sample, think of a beaker of water. I can measure the temperature of the water, and it doesn't matter. I can pour out half of it and measure the temperature again, and it'll still be the same temperature. Temperature does not depend on the amount of material present. And these are the variables that are most important to us. Think about describing an experiment to somebody. You don't want really to make your experiment depend on how much sample they took. You want to fix it some way so that you only need to report the things that are important. And these are intensive variables. In terms of gaseous systems, and for us, most all systems, the temperature, the pressure, and the molar volume are intensive variables. If we have a gaseous system, those are the only three things we need to describe to completely define it. So if you tell me what the temperature, pressure, and molar volume is, I can duplicate your setup exactly. And so these are the variables that are important. Now let's take a moment to define the universe. The universe is a system and its surroundings. So if I think about a system is a part of this universe that we've decided to study. It might be a beaker with some water in it and maybe some things dissolved in the water. That might be our system. The surroundings, though, is everything else if we're talking about the universe. So we have to be very careful here. When I say the surroundings, I mean everything in the whole universe. I mean the third moon of Jupiter also. So the surroundings is really, really hard for us to define. Now, sure enough, if that beaker is sitting in my lab, on my lab bench in the lab, and I have the immediate surroundings of a reaction going on in the beaker is probably the water that it's dissolved in, and then the beaker itself, and then the air in the room, and the bottom of the beaker is sitting on a table, so heat can be transferred to all of these places. So the surroundings, technically the surroundings is everything, including the third moon of Jupiter. But for most purposes, we are just interested in the immediate surroundings. But it is important to remember any function that depends on the entire universe, system plus surroundings, does include everything. So you can imagine some things that we're going to look at would be really, really hard if we had to look at what's going on the third moon of Jupiter. So we've defined the universe now. It's a system and its surroundings. Now, conservation of energy is an important property. It is a law of conservation of energy says that the energy of the entire universe is constant. Now, energy within the universe can move from one place to another, but it can't escape by the very definition of what we call the universe. There's no place outside the universe. So conservation of energy requires that a change in the internal energy of a system is the sum of the heat and work supplied from its surroundings. The system is made up the universe is made up of the system and its surroundings. Now, imagine the energy of state one as some value here, and then I put some heat into the system out of the surroundings. Well, the energy within the system is going to go up by the amount of heat that I put in. That's taking me to this state that I'm not really interested in much because I'm not done yet. I'm going to also put some work in to the system from the surroundings. Now, anything going into the system is defined as positive. So I want you to be careful to write it like that. Now, when I put work in, I'll get some more. Now I am finished. And so the energy from here to here, the change in energy is the heat supplied plus the work done. That's the first law of thermodynamics. Now, energy we just saw is a state function. So that would mean if I had the energy of the initial state and the energy of the final state, I could get my change in energy just by subtracting the final from the initial. Unfortunately, we don't have that. There's no way to measure absolute energy of anything. We never see absolute energy. All we see is changes in energy. So the change in energy is equal to Q plus W. Now let's look at the work function. The work is defined as minus the opposing force times the change in the distance. So important features. You do have to move something from this position to that position. That's delta L. So if nothing moves, no work is done. The force that is important is the opposing force. You do work against the opposing force. And there's a negative sign. Now, the reason for the negative sign is if we say going in a particular direction is positive, then the opposing force would be negative. And so this quantity here would be negative. I need the negative sign out here so that the work comes out to be positive when you put work into a system. Here's a little cartoon that illustrates that. I've got my guy here and here. They're both applying exactly the same force to the boxes, but this one's much bigger and heavier. It's got a much higher friction force, opposing force, than this little smaller box has. I can see over here, this guy's never going to move that box because the force he applies is not as great as the opposing force. So he's not going to do any work. This one, though, is applying a force that's greater than the opposing force. The difference between those two forces will tell you how fast this box is going to move. It actually gives its acceleration. It tells you how fast it increases per second. That's Newton's second law. But for us, we let the little guy work, and there he goes. He's moving his box over to here. Now, delta L isn't zero. The opposing force isn't zero. So he did do some work. Work is not zero in this case. So remember, work is minus the force opposing times the change in boundary. Bottom line takeaway point. If work is done, a boundary has to move. That's going to be important. So sometimes we'll know an initial state and a final state. We can look at those two and see if a boundary moved. If a boundary moved, work was done. If a boundary didn't move, no work was done. So this is the critical takeaway point from this little cartoon. Now, we're going to change some things around a little bit by multiplying this equation by area divided by area. Now, when you do that, you get force divided by area, and area times length. Well, force divided by area is what we define as pressure. For example, we call it atmospheres of pressure sometimes, and we call that 760 millimeters of mercury and all of that. But atmospheric pressure is 14.7 pounds per square inch. So any of these is actually force divided by area is pressure, regardless of the units that you put it in. Area times length, well, that's volume. So for gaseous system, work is minus P delta V. Now, P is the pressure, and again, think about it this way. The pressure has to be the applied pressure on the system from the outside. And you're doing work against that. So if that system boundary increases, pushes out against the atmosphere, then you're going to have work done, and the pressure that it works against is going to be negative. You're pushing out, right? Work's coming out of that system. So the change that in the internal energy can be measured from the heat flow also at constant volume. So we're looking at work. We saw how it happens, and we're looking at now the heat flow. Now, if you look at the change in internal energy, when the volume is constant, this work term is 0. So I put a little subscript on to talk about I'm measuring the internal energy when the volume is constant. Now we've already seen that Q and W are all state functions. They will change from one set of conditions to another set of conditions. But in this case, in this special case, the conditions are that there'll be no change in volume. Volume is constant. So if volume is delta V is 0, no work was done. So this gives us Q at constant volume is going to be equal to delta E. Now remember way back a minute ago or so, I said if I had the final energy and the initial energy, I could subtract them to get delta E. And I told you then, I don't have those absolute energies, but I can get around it. You see, delta E, the state function, can be measured only when the volume is constant. So if I measure the heat flow when the volume is constant, I have measured delta E for that process going from state 2 to state 1. The beautiful thing of this is energy is a state function. So if I measure it once, I can put that down in the back of my book and I can look it up. I never have to measure it again. The delta E will always be the same as long as I'm going from the same initial state to the same final state. While I can't measure the energies directly, that's no problem for us at all. All I have to do is measure the heat flow at constant volume. Now, you remember Q is mass times specific heat times delta T. So all I'm going to do is measure the heat capacity of my calorimeter system and the change in temperature. I can calculate the number Q at constant volume, and that is my delta E. So that's good. So not delta E is always equal to Q at constant volume. That means to get delta E, we must measure the heat flow when the volume is constant volume path. Now, I just told you it's a state function, so delta E is the same along any two paths. Now remember, we measured this along a constant volume path, and we got a number. Let's make up a number, 100 kilojoules in going from state 1 to state 2. Maybe I've chosen enough methane and oxygen to make carbon dioxide and water to give me 100 kilojoules when they burn. Now, I can do that. Let's say I did it in your Bunsen burner. Okay, then I would measure the heat flow in that process and I would get 100 kilojoules. What if I took that same amount of oxygen and methane, put it in a balloon and sparked it and caused it to explode to make the carbon dioxide and water? How much energy would be involved in that reaction? Since energy is a state function, it's the same that you did in the Bunsen burner or when the balloon exploded. Suppose I take the methane and the oxygen and I put it in a fuel cell and I have that react to generate a voltage to run my Prius or whatever. If I put the same amount of methane and oxygen through that fuel cell, it is going to produce also 100 kilojoules of energy. That would be converted into charging in the battery. Now, see what I'm getting at? Delta E is a state function. If I start with methane and oxygen to make carbon dioxide and water in that balanced equation, as long as I go between those two states, I'm going to get the same number. Suppose somebody did measure it, and it isn't, but suppose it were 100 kilojoules. Then I've got the number. I don't ever need to measure it again because delta E is a state function, independent of path. Now here's another state function. We've used it already, although we don't call it that often. Maybe we do a few times, enthalpy. But enthalpy is a state function. It includes the internal energy. Now, internal energy is a total of all the energy in a system. It depends on what's in it. If it's methane or if it's propane, it's a different value. So it depends on what it is. It depends on how much is in there to get the energy. But if we do it as kilojoules per mole, then that's okay too. That's an intensive variable. So we define the state function H, enthalpy, as the internal energy plus PV. Now this is really, really important for gases because P times delta V, remember, was work or energy. Work and energy have the same units. So this PV product in a gaseous sample can be a significant amount of energy. So the enthalpy includes all of it. It includes the internal energy, plus it includes the product of pressure and volume that we would use then to get the energy because it's a gas. And this can be significant. That's the main reason we define the new function delta H. There's another reason I'll talk about in a minute. So at constant pressure, delta E is the Q at constant pressure. So I'm measuring the change in heat in two different ways. If I measure the change in heat when the volume is constant, sometimes we do that in a device called a bomb calorimeter. It's a great big heavy steel container that we are sure is not going to explode. So that boundary is never going to move. Anything can happen inside it, but the boundary doesn't move. In that particular case, we're measuring the heat flow at constant volume. And we can do that easily with gases. Or we can do it at constant pressure. That would be like in your Bunsen burner. When you're measuring the combustion of methane in your Bunsen burner, you're measuring it out in the lab. And the gases, everything going into your burner is at 1 atmosphere pressure. Everything that's going in, everything that's coming out. So it's at constant pressure. This would be an experiment. If we measured the heat flow at constant pressure, we would get delta H. So we've got delta H here, not delta E. I did say the correct things a while ago when I said delta E would be the same for all of those processes. But when you measure Q at constant pressure, you're measuring delta H, not delta E. But they're related to each other. So Q at constant pressure is delta H. And we can look at a reaction, for example, it's P delta V. And if we think about them as ideal gases, nRT is the product of PV for an ideal gas. You remember PV equals nRT. So delta V is the change in the number of moles times RT. And so that's how we can get that into units like energy. R in this case is 8.314 joules per mole per degree, not the 0.0821 value. So all we got to do is see how many moles of gas we got in the products, subtract off the number of moles we got of gas in the reactants, and that'll give us a delta N. So multiply that by R and the temperature, and that gives you the work correction to delta E in order to get delta H. So we've got delta H is Q when you measure it at constant pressure. Delta E was Q when we measured it at constant volume. Both of them are state functions. And once you measure it once along this path, you never need to measure it again. Now, the point I made in each one of these cases is that it is a state function. So now let's go back to our Bunsen burner and bomb calorimeter example. If I measure the heat flow in the bomb calorimeter, I've measured delta E, I can record that and write it down. If I measured the heat flow in your Bunsen burner in the lab, I would measure delta H. And so I'd have a number, I could write it down. Now, what about the delta E when the process is carried out in the Bunsen burner? Here's a point that a lot of people tend to confuse. It's still the same as you measured it before under constant volume. So back up there when you wrote down 100 kilojoules for the delta E for this process in the bomb calorimeter, that's what it is in every other case. It's if we carried it out in the Bunsen burner, we can't measure delta E. But I don't need to if it's already been measured. I know what it is. What about delta H when the process was carried out in the bomb calorimeter? I can't measure delta H there, but I don't need to. I've already measured it and written it down. I measured it in the constant pressure Bunsen burner experiment. So once I get these numbers, remember both these functions are state functions. They have the value you've written down already, no matter how you carry the process out. Hope that's clear, okay? Because this is a very, very important, even critical part to understanding the thermodynamics that we're going to cover. Now, spontaneous process may occur without any intervention. Now, or anything happening from outside. Now, these are extremely important to us. I know that methane and oxygen will spontaneously explode if I ignite them. I know they'll get off energy. Well, what if I took the methane and the carbon dioxide and water and tried to put them back together? Well, that energy is already gone. That energy is already out there. It's in the universe. Carbon dioxide and water are not going to go back and make methane and oxygen because the heat has already been released when they were formed. That's a part of the energy they have now, but it's already been released. So it's important. The spontaneous processes are the ones that we can use to do work. See, your car will run on methane if you fix the carburetor and change it out and do some stuff. It'll still run on methane and oxygen, maybe even better than it does on gasoline in some cases. But that process is spontaneous is the reason why we could use it in our car. So we need to find out what spontaneous processes are and how we can spot them. So they're the ones that can do work for us. Or they can be used to drive other non-spontaneous processes. So if, for example, I made carbon dioxide and water in that process, if I can find a reactant that reacts with the carbon dioxide and water spontaneously to change them back to methane and oxygen, that process is possible. But you see, I've used a process that was more spontaneous than the one I'm trying to reverse. So you can use the energy from one process to drive another as long as it's giving off more energy than the one you're trying to drive in the non-spontaneous direction. Now, there's two basic driving forces that causes a process to be spontaneous. One is you can delocalize enthalpy or spread it out. I've used this many times. I've probably used it with you guys already. This is Pearson's law of stuff. Stuff spontaneously goes from where it is now to where it's not. So That's the spontaneous direction. If we think of enthalpy, say I've got 100 kilojoules of energy in some matter, then that energy can cause that process to take place if the energy can be delocalized and moved out somewhere else. So spreading of entropy, diluting of enthalpy rather, is one of the processes that causes things to occur. We might guess that exothermic reactions, which takes energy within the reaction and spreads it out to the universe outside, if it's exothermic, that would satisfy point number one. One of the things that drives a process is spreading the energy out. Oh, letting it go to the third moon of Jupiter. Okay. So delta H should be less than 0 or negative for this number one to be driving a process. A second and then independent one is increasing disorder. Now this might sound funny to you, but if you think about a nice pretty building with all of their bricks and everything and that make it up, that's got an organized pattern of bricks and mortar and stuff that make up that building. What if I could come back and look at that building 100 years from now? Well, chances are, if nobody's done anything to it, it'll be a pile of bricks and some sand and stuff that used to make up the building. The spontaneous spreading of disorder is one of the things that drives something like that from happening. Now, when they were building our new science building, I remember driving by several times and seeing piles of bricks and all the stuff that made up the building sitting on the lot. But you know what? If nobody had come back to that lot, you could come back 100 years from now and all those piles would probably still be there. They might have rubbled down themselves. The pile of bricks might no longer be a nice organized pile of bricks, but you're not going to see a building there. You do not get spontaneous production of order. Now think about that. Think about the universe. The universe is all spreading out and doing kinds of stuff. You are not going to see the universe reorganize itself. That's just not going to happen. So this disorder is called entropy. And a change in entropy is the change in order that's taking place. Now, let's look at some problems with this, and then we'll continue. Predict the signs of Q, W, delta H, and delta E, delta S when propane gas, C3H8, burns in oxygen at 25 degrees Celsius and 1 atmosphere pressure. Okay, here's the balanced equation. Now, is this process going to give off heat or not? Well, propane is the gas in the little big cigarette lighter, which I hope none of you use or have ever seen. But anyhow, it's the fuel. Oxidation of almost anything produces heat. So sure enough, that is going to happen. This is going to be an oxidation, and all oxidation reactions are exothermic. So this is going to give off heat. And so if it gives off heat, Q is less than 0. Remember, heat coming out of our system. Now, our system is the propane and oxygen and carbon dioxide and water that's shown in that balanced equation. And when that process takes place, it gives off heat. Heat is coming out of that reaction into the surroundings. So anything coming out is negative. Okay, let's look at the work. Work is minus P delta V, and I showed you that the that was also equal to delta N RT, where delta N is the change in the number of moles of gases. So if I look at this reaction, I've got 3 moles of gas in the reactants, or in the products. Notice water is in its liquid state. And I've got 1 mole of propane that's gas and 5 moles of oxygen that's gas. So there's 6 moles of gas in the reactants and 3 moles of gas in the products. So delta N is going to be -3. -3 times a minus out there is plus. So work is done on this process and it's gone into the system. Now let's think about the volume. I had 6 moles of gas in the beginning, so imagine a big container. I had 3 moles of gas in the product. Now the container is smaller, enough to hold 3 moles at 1 atmosphere pressure. So you can see that going from the big volume to the small volume, it would be like you pushed in onto the system to make it smaller. So work is being done on the system, and work done on the system is positive. Work going into the system or on it. Okay. Now delta H, well, delta H, we burn this stuff in air, so it's oxidative and it's going to give off heat too. And delta H is also going to be less than 0. Sort of aside, my experience has been that delta E and delta H always have the same sign. I can't think of a single example where that's not true. In fact, for some other reasons, I'd kind of like to find a process where they had opposite signs, but I can't. All right. Now, delta S is entropy, a change in entropy. Now, you will have the entropy change that takes place is going to be the same sign as delta N. So delta N up there was negative, and so delta S is also going to be less than 0. And now, let's predict the sign of delta S and delta H for this process. We've got ice, the melting of ice at 25 degrees and at -25 degrees. Which process is spontaneous? Okay, now you tell me. If you take an ice cube and set it out in a room at 25 degrees, it's going to melt, right? That's spontaneous. What if you take that same ice cube and put it in a freezer at -25?
Dr.
It's not going to melt. Yes.
Will you please excuse me? I've got a bad attitude right now.
I'm sorry, Amber, I didn't understand you.
Will you please excuse me? My attitude is bad right now.
Okay, very good. All right. I'll see you later. I'll have it up on D2L. Okay. So delta S, we've got the process. We're going from solid water to liquid water. And we're going from order. Think about what a solid is. A solid is a regular ordered pattern of particles. And the liquid, you have the particles, but they're not locked into place. They can move around on each other. You can slide one molecule of water from one place to another without much energy. In fact, it happens all the time at room temperature, but not so in solid ice. In solid ice, every water molecule is located in one particular three-dimensional point. It never moves from there. It might vibrate around in that area, but it never moves out of that position. So we've got a very ordered pattern here, a very disordered pattern here. So entropy is going from order to disorder. So that is greater than 0. And by our little second point, it would predict spontaneity in that direction. Now, if I go from solid water to liquid water, okay, what has to happen to do that? Well, if I want to melt ice, what do I have to do? I have to put heat into it, don't I? Okay, so heat's required to melt ice. So delta H is greater than 0. Aside, I've heard some people argue that water gives off heat when it freezes. Well, if you went from liquid water to solid water, the heat would be on the side of the solid water. So that's what it looks like. But I am here to tell you, freezing liquids gives off heat the same way that cows give milk. Cows don't give milk. You have to go in and take it from them. And that's the same thing. Liquids don't freeze and give off heat. You have to take heat out of them to make them freeze. All right. So this process will be spontaneous at the 25 degrees because of number 1, and non-spontaneous less than 25 degrees, again, because of the delta S term. Delta H is in the wrong sign anyhow. All right? Delta S in this particular case is more important than delta H. They're going opposed to each other. The fact that we observe melting at 25 means that delta S is the dominant one of these two. Now, what if you took silver chloride and hydrochloric acid and put them together to react? It's actually the silver ion reacting with the chloride ion to produce silver chloride solid. Now, you know that that reaction occurs. You've done it in the lab. You mix hydrochloric acid and silver nitrate, you get a nice, pretty white precipitate of silver chloride. So we know this process is spontaneous. But what about delta S? Well, let's look up here. We've got these silver ions and chloride ions just mixed in a great big volume. And they're moving around and bumping into each other and then forming the silver chloride. But what do I have on the right-hand side? I have silver ions and chloride ions packed together in a very nice ordered crystal pattern. So there's very little disorder on this side and a lot of disorder on this side. So we're going from disorder to order. Nope, that's not going to happen. Not from delta S. Well, let's look at delta H. If you have solvation of large ions is smaller than the formation of the crystal lattice. So therefore, delta H will be less than 0 on some of those. And if I'm looking at this process, and I do see it happening, delta H is wrong, but delta S predicts the correct. So in this case, the delta H is more important than delta S. Delta S said it wouldn't happen. Delta H said it would. Now, what about this process? N2 and H2 to make 2NH3. Okay, well, delta S. Again, we can look at the sign of delta N. We got we've got 3 plus 1 is 4 moles of gaseous reactants and 2 moles of gaseous products. Products minus reactants then is minus 2. So delta S is going to be less than 0. That would be non-spontaneous. Now, almost any elements that react together do so exothermically. So hydrogen reacts with a lot of things, and it usually reacts with hydrogen to produce an exothermic reaction. So delta H would be less than 0, so that would be predict spontaneous. Well, is this reaction spontaneous? Which is more important in this case? I'll have to tell you later. Now, here's your checkpoint on this lesson. And I do want you to work these checkpoints out. I wish you would use the drop box, the discussion drop box to talk to each other, but if you don't, that's okay. If you have questions, you can ask me, but be sure you do it and be sure the sign is correct. And here are number one. If you look at this one now, what are we doing? We've got the compound is burned at constant volume. So this is a constant volume process. I've given you the heat capacity of the calorimeter and the temperature. You can get the temperature change. So Cp times delta T is going to be Q. And you can calculate that, and that'll go here. And then remember, we've got a little problem with the getting work in some cases, but not here. If the volume is constant, we know what the work is. And then we can get delta E or delta H. In fact, in this one, you can get one of these two. Now this one, if the same size sample is burned in a constant pressure calorimeter, temperature goes from here to here. And this is the heat capacity of the constant pressure calorimeter. It's a different number. So now, carry out this reaction, and when you do it at constant pressure, you're going to get a Q, and that's going to also give you one of the others. So one of these two, delta E or delta H, you're going to get from experiment 1. The other one you're going to get from experiment 2. And just remember, a state function is a state function is a state function. Okay, that completes our lesson for today. If you have any questions, I'd be glad to answer them. I'm going to end the recording right now as soon as your questions are over. If any of you have questions you'd like to ask about. All right, I appreciate your coming to the meeting, and you can always reach me by email if you have questions or anything you want to ask about. You all have a good day and stay indoors and stay healthy.